welcome again to lecture number 10 of this course on solar photovoltaics. So, in the last lecture we were talking about carrier statistics in semiconductors. So, we talked about the carrier statistics. In semiconductors, we also looked at the ionization energies of dopants, and then we looked at carrier concentration relations, and finally we looked at effect of composition on effect of doping on EF. So, basically we said that for N type EF increases as compared to EFI, and for P type EF, so you can say EFN and this could be EFP, this goes down with respect to EFI, the intrinsic Fermi level. Okay, and if you plot it, it's going to look like this. So, this is your energy scale, this is let us say NA or ND, typically given in 10 to the power into centimeter cube. So, let us say if this is the value of EFI, then they tend to, and if this is let us say your EC and this is let us say your EV, okay, then Fermi level tends to, so let us say you are plotting from 10 to the power 13 to I do not know 20, 10 to the power 20, okay. So, we are going to have 14, 15, 16, 17, 18, 19, I don't know 20, 21, okay, 14, 15, 16 and so on and so forth. So, this tends to at about somewhere in this range, the semiconductors tend to become, it is almost sort of a straight line, okay, and it gets very close to, and from this side also it tends to sort of. So, when this gap is, so you can see that at very high doping level, the Fermi level, so this is EFN and this is EFP, let me put it using different this color, okay, and this would be for the P type, okay. So, you can see that as it approaches high doping levels, it tends to touch the conduction band, which means it becomes like a metal, okay. So, since the EFN and EFP get closer to EFP, EFN gets closer to EC and EFP gets closer to EV as you keep doping the material, there comes a limit when this gap is smaller than 3 kT. So, this is the limit you have of 3 kT, okay. So, when the gap is smaller than 3 kT, then what the semiconductor converts into what we call as a, so when EC minus EFN or EFP minus EV is less than 3 kT, then what we make a semiconductor is called in this case as degenerate semiconductor. It becomes like a, basically it tends to become like a metal, okay. So, essentially Fermi level is almost merged into the valence or conduction band, alright. So, this is the effect of concentration on Fermi level. Now, let us look at the effect of carrier concentration, effect of temperature on the carrier concentration. So, let us see. Temperature on carrier Now in case of, so when you plot, let us say for a n type semiconductor, n divided by let us say Nd, okay, as a function of temperature in Kelvin, okay. So n divided by Nd will be equal to 1 at certain place, and then it will be 0 at certain place, it will be half, and then it keeps increasing as you go to high temperatures, okay. So 1.5, 2 and so on and so forth. Now what happens in semiconductors is, for a, you can see that for a n type semiconductor, for an intrinsic semiconductor, Ni is proportional to exponential of minus Eg by 2 kT. So there is an exponential dependence upon temperature for the carrier concentration, and carrier concentration at finite temperatures keeps increasing exponentially as a function of. So if you plot Ni would follow a behavior like this, okay, exponential kind of behavior, Ni divided by Nd. So this is Ni by Nd, okay. Now for the same thing, if you plot for extrinsic semiconductor, then initially the carrier conductivity, the carrier concentration is very low or almost equal to 0, then it keeps increasing and then it flattens out at some temperature, and then it starts following this intrinsic behavior. So there are three regions in which carrier concentration in a semiconductor changes. The first region is called as freeze out region, and this is called as extrinsic region, and this is called as intrinsic region, okay. So initially what happens is that so what is the meaning of this extrinsic region? So when you look at this at the 0 Kelvin, at 0 Kelvin, let us say this is the situation, this is your EV, this is your EC, and somewhere here we have ED, okay. Now when the material is at 0 Kelvin, all the electrons which are sitting at ED, so when T is equal to 0 K, they do not get excited to EC, which means there is no carrier concentration, and since these carriers cannot reach here, there is nothing which can reach here also. So as a result, the carrier concentration is very close, is 0 at 0 Kelvin, and as you slowly increase the temperature, because there is a certain energy has to be crossed, the carrier concentration starts increasing only at a certain temperature, and it keeps increasing until your temperature is high enough so that all the carriers from donor levels are able to excite to the conduction band. So this is when you reach the boundary of extrinsic region, when N becomes equal to Nd, which means all the electrons which you have in conduction band are because of donor impurities, or in acceptor, in the p type semiconductor, it will be equal to the acceptor impurity concentration. So you can write this, you know, it could be equal to, so this is Ne, this could be NH divided by Na, okay, or for p type, and for p type instead of Ed you will have Ea, okay. So it continues to remain in extrinsic region until you reach significantly high enough temperature so that you are able to excite now the electrons from the valence to the conduction band in significant numbers. So when that starts happening, your intrinsic carrier concentration takes over the extrinsic carrier concentration. So you can say that in this region Ni outweighs Nd, in this region Ne is equal to Nd larger than Ni, okay. In this region your Nd is larger than Ne because you are not able to ionize Nd, okay. So you can say that this is equal to Nd plus, here you can write N. So donor impurity atoms are not ionized, as a result your electron concentration is lower in the lower temperature region. When you reach sufficient and high enough temperature, all the donor atoms gets ionized, as a result all the electrons which are in the conduction band are due to donor atoms, and hence their concentration is equal to concentration of donor atoms, but it is far bigger than the intrinsic carrier concentration because you are still in the low temperature regime. When you reach high temperatures, then intrinsic carrier starts building up in number, and soon they take over the extrinsic character. So, as a result, semiconductor always shows three regimes: freeze out, extrinsic and intrinsic. What happens at low temperature, for example? So, we looked at 0 Kelvin. At low temperature, what will happen is that you will have, so this is the valence, so this is EC, EV, ED. So, you had some electrons hopping over here, okay, and so this will perhaps correspond to this state. Let us say somewhere here EC, EV, ED, all the electrons from here have hopped over. So, this is empty, you can say this is empty, and this is, you can say, partially filled. So, all the electrons have hopped over, right, and here somewhere here at so this is, let us say, at moderate temperature, this is at moderate temperature, this is at low temperature, and at very high temperature what you will have is basically this is ED, this is EC, this is EV, this is empty, all the electrons have crossed, but even from here the electrons cross. So, they start jumping here, okay, this is at high temperature, alright, this corresponds to this region. So, this is how temperature carrier concentration varies in semiconductor as a function of as a function of temperature. Sorry? No. Low temperature. What low temperature means is that, see, EV, EC are fixed. This is the donor energy level. So, when the atoms, when the electrons, the impurities which are to which this donor level corresponds to, they do not get ionized. There is certain amount of ionization energy which is thermally provided. When the temperature is very low, then thermal energy is kT, right. When T is very low, this kT is very low. When kT is very low, you are not able to excite the electrons from here to here. So, which means there are no electrons for conduction. The electrons were supposed to come from the donor level, but they cannot move to conduction band because the thermal energy is very low. So, as you keep increasing the temperature to higher temperatures, you get enough thermal energy to overcome the ionization energy of donor atoms. As a result, the electrons from this stage, they go there, and at slightly higher temperature. So, they start going, but they do not all of them go, it is a probabilistic process, right. So, at slightly higher temperature all of them leave, at lower temperature only some of them leave, and it is within this range all of them have left. So, within this range, since once all the donor atoms lose their electrons, there is nothing more to come. As a result, the electron concentration stays flat, and you are not able to increase the Ni substantially only until you reach a certain temperature, beyond which Ni increases fast enough. So, these two curves, in some sense, if you look at the lower curve, this curve, this is the intrinsic part. So, these two curves, the top and the bottom, they are competing with each other, okay. So, what is this competition? You have to move electrons from here to here, and you have to move electrons from here to here. So, obviously, for electrons to move from valence to conduction band, you will require larger energy, and hence it happens only at high temperature. At low temperature, you are only able to excite electron from the donor to conduction band, and that is why the extrinsic behavior dominates at lower temperature, okay. And same will happen in case of p-type semiconductor. Now, let us see, having seen the effect of having seen in some detail the carrier statistics, now let us see what is the effect, what is the carrier action or carrier transport. So, just like we write for metals we write sigma is equal to Ne mu, right. where N is the electron concentration, E is the electronic charge, mu is the mobility. Now this is for metals, because we are in metals we only consider one carrier as a moving species, which is the electron. In case of semiconductor, we add another term here. So this is Ne, E, mu E. We also consider another carrier, which is NH, P, mu E and mu H. So this is the contribution from electrons, and this is the contribution from holes. Now if you say that E is equal to P and for intrinsic semiconductor, Ne is equal to Nh is equal to Ni for intrinsic semiconductor, then you can write sigma to be equal to Ni E mu E plus mu H. Okay. So depending upon the relative magnitude of mu E and mu H, one of them will dominate. However, for extrinsic semiconductor, the expression changes a bit. So we are saying that sigma is equal to Ne E mu E plus Nh P mu E. Okay. So P is the whole charge and E is the electronic charge, which are plus and minus 1 in both cases. Now let us say for a N type semiconductor, we are saying that Ne is equal to Nd, which is a lot higher than Nh, and Nh is equal to Ni square divided by Nd. So sigma N becomes in this case Nd E mu E plus Ni square divided by Nd into P, sorry, this should be Nh, P mu H. Okay. Now since this component is very small, this is small, this tends to dominate. So as a result, sigma for N semiconductor is almost equal to Nd E mu E. Similarly, for a P type semiconductor, the sigma P tends to be equal to Na E mu H. Okay. This is what the carrier concentration and the conductivity of these two semiconductors will be. Now in general, there are two methods of conduction in semiconducting materials. The first one is called as drift and second one is called as diffusion. These are the two mechanisms under which carriers move in semiconductors. Now this is the conductivity. Okay. The current that you obtain is equal to J is equal to sigma E. Okay. This is pertaining to drift part, where carriers move under the influence of electric field. But you may also have a current because of, current is because of motion of charges. The charges do not necessarily move only because of electric field. They can also move because if you have a concentration gradient. So a concentration gradient may drive the diffusion in diffusion of carriers, leading to another type of current, which is the basically diffusion current. So you have a current which is driven by a phenomena called as drift, which takes place because of electric field, and then you have so you can say dN by dx or dP Ne by dx or Nh by dx. Okay. If you take one dimensional model of these, you can also take three dimensional model, that is not a problem. So these are the two phenomena. First is drift, electric field driven, second is diffusion, that is the concentration gradient driven. So in case of drift, we won't be able to get into details of it. In case of electrons, Jn drift is basically Q mu n into N E, okay. Whereas Jp drift, it comes basically from the derivation of Ohm's law, and you can find that in any Q into mu P into P E. These are the two expressions which one can follow for drift current. Essentially, it is nothing but J is equal to sigma E, okay. Let me just, this is N E, let me just, sorry, so we are changing the terminologies, this is NH, okay. Q is the electronic charge, okay, which we took as E and P earlier. Ne is the electron concentration, NH is the hole concentration, mu n is the electron mobility, mu p is the hole mobility, and E is the electric field. So, Q is electronic charge, Ne and NH are electron slash hole concentration, and by the way, this is in Coulomb. This is typically in per centimeter cube or per meter cube. Mu n and mu p are electron or hole mobilities, which is basically E tau divided by m, okay. And this is in centimeter square or meter square. So, if this is in centimeter cube, you can say centimeter square per volt second, and then E is the electric field. This is electric field. So, the drift current, we can say this is drift current is basically nothing but Ohm's law. Now, an important parameter in semiconductor is mobility. Mobility, the standard unit, it is called as mu, and the standard unit is centimeter square per volt second, or some people also write it as meter square per volt second, okay. The typical values, let us say for silicon at 300 K. So, if you have Nd is equal to 10 to the power 14 per centimeter cube, Na as 10 to the power 14 per centimeter cube, then mu n is approximately equal to 1360 centimeter square per volt second, and mu h, what are we writing it as, mu n mu p let us say, mu p is equal to approximately 460 centimeter square per volt second. So, generally for semiconductors like silicon, the electron mobility is a lot greater than the hole mobility, whereas these mobility are significantly higher as compared to as in materials like gallium arsenide. So, gallium arsenide on the other hand will have mobility, electron mobility of 8000 centimeter square per volt second, and hole mobility of 320 per centimeter square volt second. So, gallium arsenide is a very good semiconductor, n-type semiconductor as compared to and mobility also varies as a function of temperature. So, let me just show you the plot of that. So, since the carriers undergo scattering, the scattering is because of carrier movement undergoes scattering, and this scattering could be because of lattice vibrations, which is called as thermal scattering, and then you have impurities, right, because you have dopants. So, they also cause the carriers to scatter. So, when you have this scattering taking place, then one can write and generally since mobility depends upon the relaxation time we are saying that it's mu is equal to E square tau divided by m. This tau is the relaxation time. Okay. Relaxation time means the time which is spent for a carrier between two successive collisions. So it undergoes collision with the lattice, it undergoes collision with the impurities, and higher the tau, higher the mobility will be. So this tau is expressed as 1 over tau phonon plus 1 over tau impurities. You might also have defects like dislocations, vacancies, etc., and so on and so forth. There are various contributions to it. Generally, so this tau decreases when you increase the impurity concentration or you increase the temperature, because when the temperature increases, the lattice atoms tend to vibrate more. As a result, there is more scattering of carriers, and when you increase the impurity concentration, then again the carriers tend to get scattered more. So generally, so if you look at the first impurity dependence, so if you write mu n or mu p as a function of Na or Nd, at lower concentration it is relatively flat, but at higher concentration it tends to go down. So this is would be, let us say, at about 14 per centimeter cube, and the crossover will come at about 16 or so, and then this would be at about 18 or so. This is at 300 K, and the values would be this would be about, I don't know, 1200, this would be about 300 or 400, something like that. Okay. So this is for electron and this is for hole. So both electron and hole mobility decrease as the impurity concentration increases, but they also tend to change with the temperature. The mobility, as you plot with respect to temperature, so let us say mu versus temperature, and at lower doping concentration they tend to change a little faster, and if you look at the variation, if you look at the slope of this plot, the slope of this plot is approximately 2. So it goes as t to the power minus 2.2 or so if you plot it approximately, the slope. Yeah, and so they tend to vary little faster as lower doping levels. At higher doping levels they tend to be relatively in this fashion. So you can say this is increasing dopant concentration. So dopant concentration leads to reduction in mobility, and temperature also tends to lower the mobility. So this is temperature. So this is true for both mu n and mu p. So, or you can have mu e and mu h. I think we will interchange some of these terms sometimes, but mu e is nothing but mu n and mu h is nothing but mu p. Okay. So this is how mobility varies as a function of impurity concentration and temperature. So this is the drift part, and the diffusion part would be, we will discuss in the next class. I think we have run out of time today. So we will discuss the diffusion part and other aspects of carrier concentration and their change, the current generation and recombination generation, etc., in the next few lectures. Okay. Thank you.